Hello, everyone. Today, we're diving into a topic that's increasingly critical for our tech-driven world: battery recycling. Billions of batteries, those powering everything from smartphones to electric cars, are discarded every year, often ending up in landfills. But did you know these spent batteries are actually treasure troves of valuable metals like cobalt, lithium, and nickel? Through sophisticated recycling methods, these materials can be reclaimed and reused in future technologies, from electric vehicles and renewable energy systems to cutting-edge medical devices. In this video, we'll show you exactly how the recycling process works, from the moment an old battery is collected to the intense chemical and mechanical steps that transform it into usable raw materials. You'll see how global giants like Tesla, Volkswagen, and BMW are investing in these processes, aiming for a greener, more resource-efficient future. Get ready for an eye-opening look at how dead batteries can spark new life in tomorrow's innovations. As our world electrifies, batteries are everywhere: portable electronics, EVs, renewable energy storage, and more. But with short consumer product lifespans, millions of these batteries end up trashed daily, posing environmental hazards and wasting precious metals. Traditional landfill dumping risks leaching toxic substances like lead, cadmium, and lithium into soil and water. Meanwhile, valuable components like cobalt or nickel lie buried, despite growing demand for them in high-tech industries. Governments and companies alike recognize that recycling is both an environmental imperative and a strategic advantage. For instance, lithium and cobalt supply chain constraints push automakers to secure reliable domestic sources. Recycling old batteries offers a path to do just that. In the European Union, strict regulations mandate the recycling of batteries above certain capacities, prompting manufacturers to develop local recycling infrastructure. Similarly, in certain U.S. states like California, proposed legislation aims to make battery disposal more transparent and responsible, further illustrating how policy can drive real change. Recycling starts with gathering used batteries from households, retailers, car service centers, and industrial sites. Many regions implement take-back programs or drop-off points at electronics stores. In some places, pickup services exist for large volumes of spent EV batteries or industrial cells. Once collected, batteries are shipped to specialized facilities. Here, staff sort them by chemistry: lead acid, nickel metal hydride, lithium ion, and others, because each requires a different recycling approach. Manual inspection, color-coded bins, barcodes, or even automated scanning systems help ensure that incompatible battery types don't mix and cause complications down the line. For smaller devices like laptops or handheld gaming consoles, you might find drop-off bins at big box electronics retailers. Some stores even offer store credit or discount coupons to encourage proper battery disposal. Meanwhile, for large-scale battery packs used in electric buses or commercial energy storage systems, specialized logistics companies transport these heavy units to designated recycling plants. Before actual metal recovery begins, batteries must be made safe. Technicians discharge them to lower internal voltage, reducing fire or explosion risks. Industrial EV battery packs sometimes retain dangerous energy levels, so factories use controlled discharge rigs or place modules in saline solutions to neutralize charges. In some lines, staff or robots disassemble large packs, removing casing and cables to access individual cells. This stage is labor-intensive, but necessary for advanced battery designs, like those found in Tesla or BMW EVs, where cells are carefully packaged to optimize performance and safety. Proper labeling and separation at this stage reduce contamination and improve recovery yields. Picture a Tesla Model S battery pack. It contains thousands of cylindrical cells arranged in modules. Skilled workers or increasingly sophisticated robots carefully remove these modules, label them, and prepare them for further processing. This step is crucial to avoid mishaps such as short circuits or thermal runaway events, which can occur if a still charged cell is damaged during handling. Next up is the shredding process, where entire cells or modules, depending on the facility's approach, are broken down into smaller pieces. This mechanical shredding liberates the internal components, metal casings, foils, electrode materials, cathodes and anodes, plastics, and electrolytes. Shredders might operate in inert atmospheres like nitrogen to minimize fire risks. Afterward, a series of screens, magnetic drums, eddy current separators, and air classification systems sort materials by size, density, and magnetic properties. The result? Streams of steel casings, copper foils, aluminum, plastics, and a black powder often called black mass, a mix of lithium, cobalt, nickel, and manganese from electrode coatings. In some state-of-the-art facilities, robotic arms feed batteries onto conveyor belts that move into large shredder units. Sensors may detect and quickly remove any battery that hasn't been fully discharged, redirecting it to a safety station. This level of automation reduces the need for manual checks and boosts overall throughput. Black mass is the heart of battery recycling. It's a dark powder containing the valuable metals crucial for new battery production: cobalt, Co, lithium, Li, nickel, Ni, manganese, Man, and sometimes graphite. Extracting these metals from the black mass is central to turning junk batteries into high-value resources. Think of it as the modern-day equivalent of mining, only we're mining old batteries instead of the earth. In the next steps, advanced chemical methods, hydrometallurgy or pyrometallurgy, help refine and separate these metals with high purity. One innovative startup in Canada has developed a proprietary process for extracting nearly 95% of valuable metals from black mass. They mix it with specific acids under carefully controlled conditions, recovering lithium and cobalt that can be directly sold to battery manufacturers. Hydrometallurgy is a wet chemical process where black mass dissolves in strong acids or bases. Common flows involve acid leaching, using sulfuric or hydrochloric acid to dissolve the metals into solution. Leaching: the ground black mass is mixed with acid at controlled temperatures and pH. This step dissolves metals into a liquid solution. Solvent extraction or precipitation: adjusting pH or adding reagents precipitates specific metals like cobalt or nickel out of the solution. Purification and drying: filtered and rinsed solids are dried into metallic salts or oxides. Hydrometallurgy is relatively energy efficient, operating at lower temperatures than smelting. It also yields high recoveries of metals, making it popular for advanced battery recycling lines. Imagine a large industrial vessel with an automated pH monitoring system. The operator can add neutralizing agents like sodium hydroxide based on sensor readings. If cobalt concentration is high, they might tweak the solution chemistry to precipitate cobalt first. filtering it out separately before moving on to nickel or other elements. Pyrometallurgy, or smelting, is an older but robust technique. Black mass is heated in furnaces at temperatures often exceeding 1,000 degrees Celsius, 1,832 degrees Fahrenheit. Metals melt or vaporize into different phases: slag, silicates, aluminum, and some contaminants gather in a glass-like byproduct. Metal alloys. Heavier metals like nickel, cobalt, and copper form alloys at the furnace bottom. Dust collection. Some volatile metals or compounds can be captured in the off-gas filters. Refiners then separate alloys into individual metals via further refining. Though energy-intensive, pyrometallurgy can handle mixed input streams, like consumer electronics with multiple metals, but might lose some lithium or other lighter elements. A traditional metal refinery might use the same high-temperature furnaces that process scrap steel or copper. By tweaking the furnace atmosphere and temperature profile, operators can recover nickel and cobalt from shredded battery material. However, capturing lithium often requires additional processing steps or a hybrid approach that combines both pyro and hydrometallurgical techniques. Both hydrometallurgy and pyrometallurgy eventually yield intermediate compounds, metal oxides, sulfates, or alloys. Further refining steps turn these into high-purity materials suitable for new battery cathodes or other high-end applications. Chemical precipitation, electro-refining, or advanced crystallization methods isolate metals like cobalt or lithium to purity levels above 99%. Many battery makers want these recycled metals to match virgin mine standards. That way, they integrate seamlessly into new battery cathode powders, lowering reliance on raw mining and enabling circular supply chains. Picture a specialized refining facility that performs an electro-refining process on cobalt alloys. By submerging the alloy in an electrolyte solution and applying an electric current, impurities gradually separate out, allowing purified cobalt to deposit onto cathode plates. After repeating this method for other metals such as nickel or copper, you end up with distinct high-purity elements that can be sold directly to battery manufacturers. Once purified, metals re-enter the manufacturing pipeline. Cathode manufacturers blend them into battery-grade materials like lithium nickel manganese, cobalt oxide, NMC or lithium iron phosphate, LFP. Automakers such as Tesla or Volkswagen can incorporate these recycled metals into EV battery packs, effectively giving old batteries a second life. Beyond EVs, recovered lithium might also find use in wind turbines, lithium-based lubricants, or cobalt could be used in medical device batteries. This cyclical approach fosters a more sustainable ecosystem, letting crucial resources keep circulating. A startup in Europe recently began supplying high-quality recycled nickel to a solar energy storage manufacturer. The same nickel that once powered smartphones is now part of large-scale battery units supporting residential solar systems. This demonstrates how old devices can indirectly promote the expansion of clean energy projects. Recycling addresses not just material scarcity, but also environmental concerns. Proper disposal prevents battery chemicals from contaminating landfills, reduces greenhouse gas emissions from raw mining, and protects communities from toxic exposure. Many recycling facilities operate under strict regulations to manage potential pollutants like battery acids or heavy metals, enforcing comprehensive wastewater treatment and emission controls. Meanwhile, Reusing metals drastically cuts energy consumption compared to mining virgin ores. This means fewer open-pit mines, less deforestation, and lower carbon footprints, a boon for eco-conscious consumers and governments. In regions where mining activities have historically led to polluted waterways and deforestation, transitioning to robust recycling programs can significantly alleviate these pressures. Reduced demand for newly mined metals lessens the ecological footprint and supports local wildlife habitats. In addition, tighter emission controls at recycling plants help maintain clean air standards for nearby communities. Until recently, battery recycling was often limited to lead-acid automotive batteries, but the surge in lithium-ion EVs and consumer electronics drives massive investment in advanced recycling. Several startups, established metal refineries, and automakers are building or expanding recycling plants. Tesla partners with specialized recyclers to recover battery metals. Volkswagen invests in pilot recycling lines in Germany, aiming for closed-loop supply. BMW works with global suppliers to ensure end-of-life lithium-ion cells funnel into recycling systems. Governments also fund pilot projects to scale emerging technologies, bridging lab research to commercial viability. In China, a major EV market, government grants have spurred the construction of large recycling facilities adjacent to automotive manufacturing hubs. This co-location strategy reduces transportation costs for spent batteries and speeds up the turnaround for recycled metals to be reused in new car batteries. Despite progress, obstacles remain. Collection rates for consumer electronics are low, and few global standards exist for battery pack design to facilitate easy disassembly. Some processes remain expensive or yield inconsistent product purity. There's also competition for scrap supply if EV batteries last 8 to 10 years or more, delaying large volumes of feedstock. R&D continues, aiming to reduce chemical usage, improve automation, or design batteries that are simpler to recycle, using standardized cell shapes, easy-to-remove modules, etc. Collaboration between automakers, waste managers, and policymakers is vital to ensure a robust, streamlined chain. Consider your average family's junk drawer, where old phone batteries and random electronics accumulate. Without convenient local drop-off points or mail-in programs, these items may never reach a proper recycling facility. Improving public awareness and establishing consistent global standards like color-coded labels or universal battery designs would significantly enhance collection rates and disassembly efficiency. Battery recycling embodies the circular economy concept, extending material life cycles and minimizing waste. By turning old batteries into refined metals and reintroducing them to the production of new cells, we cut reliance on virgin mining and mitigate environmental damage. The promise is that every end-of-life battery becomes the resource for tomorrow's energy storage, forging a loop that underscores sustainability. As governments set ambitious electric mobility targets, tapping recycling's full potential ensures these transitions remain affordable, feasible, and eco-friendly. In a circular economy model, an electric bus fleet in a major city could systematically replace spent lithium-ion packs with newly refurbished ones. The old packs go into recycling, which recovers essential metals. These metals return to battery manufacturers who create fresh cells, completing the loop. This cradle-to-cradle approach keeps material circulating in the industry instead of heading to landfills. Tech-savvy solutions like AI-driven sorting, robotics for disassembly, or lower-temperature hydrometallurgical processes can boost yields, reduce hazards, and trim costs, some labs experiment with direct recycling, where entire cathodes are regenerated without decomposing metals fully. If commercialized, such direct cathode recycling could skip multiple refining steps. Data analytics and digital tracking tools also help. Knowing a battery's composition upon arrival at the recycling plant simplifies the process, improving throughput. Safety protocols, like automated inert gas chambers, minimize fire risk from damaged lithium cells. Imagine scanning a QR code on an EV battery module. That code reveals the exact chemical makeup and history of the battery. With this data, the recycling plant's AI system automatically sets the optimal discharge procedure, shredding protocol, and chemical extraction settings, saving both time and resources. Finally, the success of battery recycling depends on consumer participation. Whether returning worn-out phone batteries or dropping off EV packs at designated sites, everyday choices shape supply feed. Public awareness campaigns highlight the dangers of landfill disposal and the value of recycling. Some electronics retailers offer incentives or store credit programs to encourage returns. This synergy between individual action and industrial capacity cements the loop. From our hands, dead batteries travel to specialized plants, re-emerging as new resources that fuel the next generation of innovations. Local community events, such as e-waste drives, can significantly increase the volume of batteries collected. By partnering with municipalities, schools, and nonprofit organizations, recycling advocates ensure that the public knows where and how to dispose of old batteries safely. We've ventured through the intricate world of battery recycling, seeing how old cells can become fresh metals for electric cars, wind turbines, medical devices, and more. If only my Monday morning energy could be recycled the same way, I'd be unstoppable by mid-week. From careful collection and disassembly to shredding and advanced refining, the process stands at the forefront of modern sustainability efforts. Big-name automakers and tech giants invest heavily in these systems, convinced that recycling is key to a future with limited raw mining needs and greater resource independence. If you found this deep dive insightful, consider subscribing for more explorations into how our modern world manages waste and transforms it into the building blocks of tomorrow. Share your thoughts in the comments. Every perspective enriches the conversation. And next time you see a dead battery, remember, it's more than trash. It's a potential treasure, ready for a second life in the technologies shaping our collective future.